everybody. Today I want to show the knowledge about the blow molding. Modern blow molding technology originated in the 1930s. After years of development, it has developed into the third largest plastics processing method after injection molding and extrusion. Compared with injection molding, blow molding technology has and cost and can form complex hollow products. Hello, friends, welcome. Is widely used in the packaging, soft material industry, toys, automobile manufacturing, and other industries. Here we first give an overview of the more commonly used blow molding technology. Injection stretch blow molding. Injection stretch blow molding technology is currently more widely used than the injection blow molding. This is blow molding method is actually injection blow molding, but is action structure, which makes blow molding easily and reduce energy consumption. The volume of products that can be processed by injection stretch blow molding is larger than that of injection blow molding. The volume of the blown container is 0.2 to 20. The working process is as follows. First, inject the perform. The principle is the same as ordinary injection molding. Then transfer the perform to the heating and temperature adjustment process to soften the perform. Transfer to the stretching blow station and close the mold. The push load in the core stretches in the perform axis and blows air to the make the perform close to the mold wall and quiet. Transfer to the demolding station to take out the parts. In addition, extrusion stretch blow molding is also very common and is even more widely used than injection stretch blow molding. Unlike injection stretch blow molding, is molded pollution is formed by extraction, with excess material and flash, and low injection stretch blow molding with high precision. Whether it is injection blow molding or injection stretch blow molding, extraction stretch blow molding is divided into one-time molding and two-time molding process. The one-time molding method has a high degree of automation, and the clamping and transfer system of the precision requires high precision, and the equipment cost is high. Generally, most manufacturers use the two-time molding method. That is, the pressure is first formed by injection molding or extrusion, and then the pressure is placed in another motion, injection blow molding motion or injection stretch blow molding motion. To blow out the finished products, with high production efficiency. Injection blow molding. Injection blow molding is the most widely used blow molding method in blow molding. It can be processed in a wide range, from small products to the large containers and automotive accessories, aerospace, chemical products, etc. The processing is as follows. First, melt the rubber material, mix it, and then the melt enters the head to become a pear-shaped preparation. After the perform reaches the predetermined lace, the blow mold closes and clamps the perform between the two halves of the mold. Blowing air into the perform, inflating the perform so that it is close to the mold cavity for molding. Cooling the product, opening the mold and taking away the cold and hardened products. Injection blow molding. Injection blow molding is molding the method that combines the practice of injection molding and blow molding is currently mainly used for blowing beverages of bottles and medical bottles with high precision requirements and some small structure parts. In the injection molding station, the perform is first injected, and the processing method is the same as the ordinary injection molding. After the injection molding is opened, the core load moves to the blow molding station together with the perform. The core load process the perform between the blow mold and the closed mold. Then compressed air is blown into the perform through the middle of the core load, inflating it to the make it close to the mold wall and cooling it. Open the mold. The coarse load is transferred to the molding station, and after the blow mold part is taken out, the core load is transferred to the injection station for the circulation. Injection blow molding has the following advantages and disadvantages. Advantages: the product stress is relatively high and the precision is high. Low joint seams are formed on the container. Low chimney is required. The transparency and the surface finish of the blow molded parts are good. It is mainly used in hard practice containers and wide mouth containers. Disadvantages: the equipment cost of the machine is very high, and the energy consumption is large. Generally, it can only form containers with relatively small values, less than 500, and can't form containers with complex shapes, and is difficult to form over products. Blow molding product design overview. Blow molding products are widely used in various industries, especially in the beverage and packaging industries. They are also widely used in the toy industry, such as blow-molded baby bottles, hollow floating parts, Christmas landscapes, toy children's learning driving accessories, and some large toys such as slide trucks, bases, etc. With different parts requirements. The focus of products design is also different. For toy products, blow molding products are more focused on safety and physical testing, pulling, twisting, zoning, and stress cracking considerations. While for container products, more attention is paid to precision resistance, corrosion resistance, and good barriers properties. Generally, the cancers and edges of the blow-molded products should be made into a transition. For example, the load containers, the minimal R of the colors is 1.10 of the container diameter. The R transmission of the product can make the whole thickness of the products uniform. The large the blowing material at the sharp corners, the easier it is cause uneven wall thickness. In addition, the sharp corners are also prone to process cracking. In addition, with different product requirements, some structure designs in terms of compression, tension, and traction can also be adapted. For example, if you want to increase the precision resistance of the product, you can design some reinforcement ribs along the force direction. If you want to improve the anti-collapse performance of the products, you can also design the surface into a arc structure that is conductive to force the supplemented with the reinforcement ribs. The shoulders of the bottom products should be included and not too straight. Generally, the bottom of the bottle is made into a concave shape to increase strength and placement stability. For example, the bottles for and oil that we usually. Hello friends, welcome. In addition to increase the strength of the bottom body, is also conductive of lapping. In structure to blow molding materials, the development and application of blow molding technology are also extensive because of the development of blow molding material. Blow molding material has gradually developed from the initial LDPE, PET, PP, and PVC products to blow molding engineering practice, rubber, and some composite material. Special requirements for rubber materials in various blow molding material. For extraction blow molding, since blow molding is carried out in various flow states, parties with larger molecular weight are usually used to reduce the sake of the pressure or optimize the whole the wall thickness distribution. For injection blow molding is carried out in a high stress in order to reduce the energy consumption of the injection molding operation. Some easy-to-flow plastics with small molecular weight and are used. For injection blow molding, non-plastics are generally used because the first of the non-plastics is smaller and easily to stretch. Although PET also stainless is still the main stretchable molding material and is quite slow. In short, most blow molding grade plastics has a medium to high molecular weight distribution. Introduction to blow molding materials. Blow fields such as HDPE, LLDPE, LDPE, PP, EVA are generally used for blow molding industrial products, containers and accessories, storage containers for chemical, etc. Thermoplastics, polyester, PETG and PETP are mainly used for blowing carbonated beverage packaging bottles, wine bottles, etc. and have gradually replaced by PVC and are widely used. The disadvantage is that they are more expensive and are mainly used for injection blow molding. Energy plastics ABC, SAM, PS, PA, POM, PMMA, PPO, etc. has been gradually used in the automotive, home appliance, chemical and other industries, especially PC, and is bending plastics, which can be blown into high-end containers and automotive products. Blow molding of the silver plastics, etc. SBS, SEBS, TPU, TPE, and other blow molding materials are usually used. However, thermostic plastics, rubber and cloth-linked PE cannot be molded. Extrusion blow molding is the most widely used and can be used to form small to large containers. Almost all blow molding grade raw materials can be processed by extrusion blow molding. Common materials for injection blow molding are PE, PET, PVC, PP, PC, and POM, which are mainly used for containers and structure parts with high molding precision and small volume. Common materials for injection blow molding are PTP, PVC, PP, PAM, especially PTP, while PC, PS, and PA can also be used for this process. Almost all blow molding grade engineered plastics have high gloss capacity and need to be pre-jarred before processing, especially PET, PC, PA. Drying has a great influence of the appearance quality of the mold. of the product, and the materials should be dried in a closed drawer. The mold usually only has a cavity part without a punch. The mold surface generally does not need to be hardened. The inflation precision of the cavity is much smaller than that of the injection molding. Generally, 0.2 to 1.0 mpg. The mold cost is low. Mold material used made of aluminum alloy and for corrosive rubber materials such as PVC and POM. Copper or copper-based alloy are also used. For molds with high life requirements such as blow molding engineering practice, ABS, PC, POM, PS, PMMA, stainless steel is required to make molds. Key points of mold design. The part surface is generally placed on the scissor plan to reduce the blow-up ratio. For example, the parting surface is on the non-axis, and for angular products is passed through the central line. The surface of the cavity should be slightly rough, especially for P materials. The fine sand surface is conductive to exhaust for blow molding of engine plates, ABS, PS, POM, PMMA, nylon, etc. The mold cavity generally cannot be sandblasted. Exhaust grouts can be made on the mold cavity parting surface, or exhaust holes can be made on the cavity. The diameter of the exhaust hole on the cavity is generally 0.1 to 0.3, and the length is 5.5 to 1.5 millimeters. For large products, exhaust needles are widely used during a large hole, inserting a needles in the hole and exhausting the air through the gap between the exhaust needles and the holes. Cavity size. The design of the cavity size should be taken into account to the shrinkage rate of the plastic. The cutting edges and tail materials glow are typical features of the injection blow molding mold. Generally, for blow molding engine plastics and harder plastics, the cutting edge should be made of wear-resistant materials such as blooming copper and stainless steel. For softer plastic parts such as LDPE and EVA, aluminum alloy is generally sufficient. The cutting edge should be of a reasonable size. If it's too small, the stretch of the joint would be reduced. If it's too large, it will not be able to cut, and the clamping of the parting surface will be large. The tail materials glue is opened by below the cutting edge. The tailed material glue is designed to be angled. When cutting, a small amount of the mold can be squeezed into the joint seam thereby improve the stress of the joint seam. For bottle products with sealed, the excess materials of the bottle mouth is cut off by the motor cornea and shock blocks. The air in the lid is also determined the size of the inner determinant of the bottle mouth. The design of the injection blow moldings is different from that of extrusion blow molding. The main difference is that injection blow molding don't require cutting blades and material grease. The design of the pollution of the injection blow parts is very important and is directly relative to the quality of the finished parts. Injection blow mold pollution designed pretty simple, long diameter less blow material work thickness. According to the shape of the products, the wall thickness should be thinner where the blow radius is large, and thinner where the blow radius is small. For containers with a radius greater than 2.1, the core load needs to be designed to be elliptical. For products with a radius less than 2.1, a long load code can be used from a container. The injection blow molding mainly introduced to its two main structures, the core load and the mold column. The core load is also the convex mode of the perform. Is also just the injection performed from one station to another. The core load is made of hardness carbon tool steel. Its surface should be polished along the streaming direction. If it has high requirements, it should be hard plated. There are blowing holes and temperature consistency in the middle of the core lid. The function of the core is to fix the core load to the valve and protect the sealed parts of the injection molding to avoid its deformation. While the mold cavity is the molding structure of the product shape and size. Its material selection has been briefly described above. Type of injection performed has. There are three forms as shown in the figure. Strand basic process of blow molding machine. The automatic air ring injection clearly adopts a double air outlet design. Among them, the volume of the lower air outlet is like a stream that forms constantly, which is consistent and provides a stable foundation for the entire system. At the upper air outlet, there are several air ducts finely distributed on the circumference. Next ducts, each air duct contains components such as air chamber, valves, and motors in an orderly manner. Okay, that's all the knowledge I wanted to show you today. The next time my colleague will show you some knowledges. Welcome.
Hello everyone, I'm Leah from Novo. Today, welcome to our broadcast room. Our company, Novo, the smart manufacturing business specializes in providing customers with projects supporting services, including parts machine and manufacturing. We have accumulated rich experiences in many innovative fields, such as intelligent care products, medical devices, automobile products, robots, and automation equipment. We attach great importance to R&D and innovation. By the end of 2023, we have obtained 2 invention patents, 23 utility model patents, and 7 documents copyrights. Noble has been assessed as a national high-tech enterprise, specialized and sophisticated SME, innovative SME by the government. Today, I will introduce injection molding to you. Uh, Next, injection molding technology occupies a pivotal position due to its advantages of high efficiency, flexibility, low cost, and the ability to produce complex shaped parts on a large scale. From the plastic products in daily life, such as water cups, cell phone cases, home appliance shelves, to the precision parts in automobiles, aerospace, and medical equipment, injection molding technology is everywhere, profoundly affecting our production and lifestyle. Next, we will introduce the basic principles of injection molding technology, development history, key technologies, application areas, and future trends to take you a glimpse of this precision process to shape the future. First, overview of injection molding technology. Injection molding, known as injection molding, is the way of inject molten plastic into the mold cavity. After cooling and curing to get the desired shape of the product manufacturing method, its basic principles can be traced back to the rubber processing industry in the late 19th century. But the real sense of injection molding technology until the mid-20th century with the rise of the plastics industry and the rapid development of injection molding process can be roughly divided into the following steps: raw material preparation, injection mold filling, cooling and shaping, demolding and subsequent processing. Second, the development of history. The development of injection molding technology is the result of scientific and technological progress and market demand. In the early days, the injection molding machine is mostly manual and semi-automatic operation, low production efficiency, and limited precision. With the continuous progress of electronic technology, hydraulic technology, automation control technology, injection molding machine gradually realized the full automation, high precision injection molding machine gradually and high efficiency production. Especially in recent years, the application of intelligent and digital technology, such as injection molding machine, network monitoring, big data analysis, and to optimize production parameters, AI-assisted mold design, etc., further enhance the level of intelligent injection molding production and the product quality. Third, the key technology analysis. Injection molding machine technology is the core equipment of injection molding technology, and its performance directly affects the product quality and production efficiency. Modern injection molding machine adopts high precision servo drive system, which can realize rapid response and precise control of injection pressure, speed, temperature, and other key parameters to ensure product consistency and stability. Mold technology. Mold is the key tool for injection molding, and its design and manufacturing level directly determines the shape accuracy, surface quality, and production efficiency of the product. Modern mold design using CAD, CAM, CAE technology can quickly complete the design of complex molds, simulation analysis, and optimization. At the same time, the application of high-precision machining equipment such as CNC machining centers, EDM machines, etc., to ensure that the mold manufacturing accuracy and service life. Plastic materials. The development of injection molding technology is also inseparable from the innovation of plastic materials. With the progress of science and technology, new plastic materials are emerging, such as high-performance emerging engineering plastics, biodegradable plastics, nanocomposite materials, etc. These materials not only have excellent physical properties but also meet the environmental protection, lightweight, and other modern industrial needs. Process control. In the injection molding process, the control of temperature, pressure, time, and other process parameters is crucial. Modern injection molding technology realizes real-time monitoring and precise adjustment of these parameters through advanced control system, effectively avoiding the generation of injection molding defects and improving the qualification rate of products. Fields of application. The application areas of injection molding technology are extremely wide, covering almost all industries that require plastic products. The following are some of the main application areas. Consumer electronic. Most of the parts such as shells, buttons, connectors, etc. of electronic products such as cell phone, tablet PCs, notebook computers, etc. are injection molded. Home appliance industry. The shells and the internal parts of refrigerators, washing machines, air conditioners, and other home appliances such as fan blades and motor mounts are also important application areas for injection molding technology. Automobile manufacturing. Injection molding technology plays a key role in the manufacturing of automobile interior parts such as instrument panels, door panels, exterior parts such as bumpers, lamp housings, and some functional parts such as fuel tanks, water tanks, medical devices. Injection molding technology is favored for its ability to produce high precision, stellar, corrosion-resistant products in the manufacture of syringes, infusion sets, artificial joints, and other medical supplies. Packaging industry. Plastic bottles, caps, trays, and other packaging materials cannot be separated from the production of injection molding technology. Future trends. Looking to the future, injection molding technology will continue to move towards intelligent, green, and efficient direction, especially intelligent with the deep application of industrial internet, big data, artificial intelligence, and other technologies. Injection molding production will achieve a higher degree of automation and intelligence, including intelligent scheduling of production plans, automatic detection of product quality, predictive maintenance, and so on. Greening, increased awareness of environmental protection has prompted the injection molding industry to continue to explore more environmentally friendly materials and production methods, such as the use of biodegradable plastics, optimize the mold design to reduce material waste, the development of low-energy injection molding machines, efficient through technological innovation and process optimization to further improve the injection molding production efficiency, shorten the production cycle, reduce production costs to meet the market demand for rapid response and high-quality products. In short, injection molding technology as an important part of modern manufacturing industry. Its development history witnessed the progress of human industrial civilization. In the face of the future, injection molding technology will continue to innovate and move forward to provide more efficient, accurate, and environmentally friendly solutions for various industries and jointly shape a better tomorrow. As an important plastics processing method, the key technologies of injection molding technology cover a number of aspects, including injection molding machine technology, mold technology, plastic material selection and processing technology, process control technology, and so on. These key technologies will be introduced in detail below. First, injection molding machine technology. Injection molding machines is the core equipment of injection molding technology. Its performance directly affects the quality of products and production efficiency. Temperature control. The injection molding process needs to control a number of temperature parameters. The advantages of injection molding. Many manufacturers turn to injection molding because it allows for complex geometries with tight tolerance. Injection molding allows for large volumes of uniform, complex parts. However, you must pay attention to vent and gate placements, weld lines, corner transitions, wall thickness, ribs, and both design, and more to its ejection to and achieve precise parts. With injection molding, you can easily achieve repeatable part tolerances of plus or minus 0.5 millimeters. In some cases, you can even produce parts with tolerance of plus or minus 0.125 millimeters, giving you parts that are accurate enough and for most applications and comparable to 3D printed or CNC machined parts. Second, it's compatible with a wide range of materials and colors. Today, there are over 25,000 engineered materials that are compatible with injection molding, including thermoplastics, thermosets, rings, and silicons. With, with all of these options, you will be able to find one that offers the right balance of physical, mechanical, and chemical properties. Commonly used materials include alkali, ABS, polystyrene, PS, and PP. You can also use a mixture of materials to produce a part with the strength, impact resistance, or stiffness you need. For example, you might add glass fibers to your thermoplastic to create a strength-enhancing composite. You also have a variety of options when it comes to colors. Consider using master batches, pre-colored rings, liquid colorants, or salt and pepper blends to achieve your desired color. It's very efficient. While it can take several minutes or even hours to 3D print or CNC machine a single part. Most injection molding cycles only last 10 to 60 seconds. Even if you have a complex geometry that takes around 120 seconds to mold, you can include several smaller parts in one larger mold. This helps maximize efficiency and get the most out of each mold, allowing you to create hundreds of identical parts an hour at low cost. Fourth, it offers high repeatability and reliability. One of the main benefits of plastic injection molding is its high repeatability. Once you create your mold, you can produce thousands of parts before needing a material tooling. Aluminum mold will generally last between 5,000 and 10,000 cycles, and a full-scale steel production mold can last for over 100,000 cycles. Plus, since injection molding uses the same mold for each part, you will have identical products. Fifth, you can reuse material. Though injection molding generates less post-production material waste than many other manufacturing processes, it still creates excess scraps. However, you can easily regrind and reuse and spoils, runners, or other leftover plastic parts to save on material and reduce material waste. The disadvantages of injection molding. There are plenty of advantages of plastic injection molding, but it's not without its drawbacks. Some disadvantages include startup costs are high. Since the customer tooling must be created from each injection molded part. Initial startup costs are high, and this isn't economical for low volume production runs. Tooling for a simple design and a small production run can cost between $2,000 and $5,000, but tooling for large complex molds ready for full-scale production can cost several times that. Although you can reuse these molds again and again and save on tooling costs down the line, it's worth considering how much molds cost upfront. An injection molding manufacturing partner can help you maximize your budget and refine your mold design so you can produce the best possible part for the best price. Second, initial lead times are long. A CNC machined part can be delivered within 5 to 10 days, and industrially 3D printed parts often have lead times of 3 to 5 days. However, injection molding has a longer lead time. It often takes 5 to 7 weeks to manufacture tooling and 2 to 4 weeks to produce and ship parts. In part, this long lead time can be attributed to the complexity of the molds themselves. In addition to containing the negative of the part, these molds have complex runner and water cooling systems of facilitate material flow and faster cooling. It can take months of design and testing before the final mold is ready for production, and any design changes can further increase turnaround times. With the help of a manufacturing partner's expertise, you can avoid falling into common mold pitfalls that might set you back weeks and thousands of dollars. They can also help accelerate the design, testing, and production phases and production phases. Design changes are expensive. With 3D printing, you can simply upload a file and print a new part whenever you make a design change. But that's not the case with injection molding. If you make a design change, you will likely need to create a new mold from scratch, which means pouring more time and money into your project. To avoid costly design changes and ease the molding process, avoid undercuts and sharp edges, ensure wall thickness are uniform, and add draft angles. If you need some guidance, an experienced manufacturing partner can offer expert design advice. Benefits of injection molding. High volume manufacturing plastics. Injection molding is the most cost competitive technology for manufacturing high volumes of identical plastic parts. Once the mold is created and the machine is set up, additional parts can be manufactured very fast and at a very low cost. The recommended minimum production volume for injection molding is 500 units. At this point, economies of scale start to kick in, and the relatively high initial costs of tooling have a less permanent effect on the unit price. Wide range of materials. Almost every thermoplastic material and some thermosites and silicons can be injection molded. This gives a very wide range of available materials with diverse physical properties to design with. Parts produced with injection molding have a very good physical properties. Their properties can be tailored by using additives, for example, glass fiber, or by mixing together different pellets, for instance, PC or ABS blends, to achieve the desired level of strength stiffness. A very high productivity. The typical injection molding cycle lasts 15 to 60 seconds, depending on the size of the part and the complexity of the mold. In comparison, CNC machining and 3D printing might require minutes to hours in order to produce the same geometry. Also, a single mold can accommodate multiple parts, further increasing the production capacities of this manufacturing process. This means that hundreds of identical parts can be produced every single hour. Limitation of injection molding. High startup cost for tooling. The main economic restriction of injection molding, the high cost of tooling, since the customer mold has to be made from each geometry. The startup costs are very high. Second, the design changes are costly. After a mold is manufactured, it's very expensive to modify. Design changes usually require the creation of a new mold from scratch. For this reason, correctly designing a part for injection molding is very important. Next, common injection molding defects. Most defects in injection molding are related to either the flow of the melted material or its non-uniform cooling rate during solidification. First is warping. When certain sections cool faster than others, then the part can permanently bend due to internal stresses. Second is the sink marks. When the interior of a part solidifies before its surface, a small resizing and otherwise flat surface may appear, called a sink mark. Drag marks. As the plastic shrinks, it applies pressure on the mold. During ejection, the walls of the part will slide and scrape against the mold, which can result to drag marks. Second is bosses. Bosses are very common in injection molded parts and are used as points for attachment or assembly. They consist of cylindrical projections with holes designed to receive screws, threaded inserts, or other types of fastening and assembly hardware. A good way to think of both is as a rib that closes on itself in a circle. Next is snap fit joints. You can use this way to deal with these problems. Snap fit joints are very simple, economical, and rapid way of joining two parts without fasteners or tools. A wide range of design possibilities exist for snap fit joints. Crash ribs. Crash ribs are small protruding features that deform to create friction when different components are pushed together, securing their position. One of the biggest benefits of injection molding is how easily complex geometries can be formed, allowing the single part to serve multiple functions. You can use a constant wall thickness and avoid thick section. This is essential as long uniform walls can lead to warping over the part as the melted material cools down. Hollow out thick sections is another way. Thick sections can lead to various defects, including warping and sinking. Limiting the maximum thickness of any section of your design to the recommended values by making them hollow is essential. You can also add some smooth transitions. Sometimes sections with different wall thickness cannot be avoided. In these cases, use a chamfer or fillet to make the transition as smooth as possible. Similarly, the base of vertical features must also always be rounded. Not round all edges. For interior edge, use a radius of least 0.5 the bore thickness. For exterior edge, add a radius equal to the interior radius plus the wall thickness. This way you ensure that the thickness of the walls is constant everywhere, even at the corners. Adding to this sharp corner in stress corner transitions, which can result in weaker parts. Cost reduction tips, such as adhere to the straight pull mode design. Tips to strategically redesign injection molded part to eliminate undercuts. Okay, our introduction is ended. Welcome welcome to our broadcast room. Minimize the size of injection molded parts. Tip 4. Optimize mold design by incorporating multiple parts.